Hi, everyone. Welcome back. And we're going to do a video lesson today for multiplication and division of radicals. They both follow very similar rules. But in this one, we're actually going to focus more on the multiplication side rather than the division side. This also plays into the simplification of radicals, which we saw back in 7.1 and 7.2 a little bit, but in this one, we're going to kind of see how it works in reverse, and hopefully you'll see the connection between the two, sort of the principles that we use when we simplify radicals. So let me switch over to our screen here so you don't have to look at me and you can see my whiteboard. And I just want to start off with kind of the idea here. And it actually helps if I show it to you from the standpoint of what we've already done, which is the simplification of radicals. So for example, let's take the square root of 50. 50 is something that does have some perfect squares that go into it. In fact, 25 is the largest perfect square that goes into 50. 9 doesn't go into it, 4 doesn't go into it. So I can break this down into 25 times 2. Basically, times 2. And so basically, all I've done is kind of rewritten that number 50. I've actually factored it, right? We've written it as a factor, which means a factor is just the expressing of something as a multiple of. So all I've done is rewrite 25 as 25 times 2. Now, we're going to see today how we're actually able to break this thing up. And so what we saw earlier is that we could just break this up into two separate statements, square root of 25 times the square root of 2, and that square root of 25 can be carried out, giving us 5 square roots of 2. And so that's the simplified version of the square root of 50. And so here's the general rule of multiplication when it comes to radicals. Multiplication of radicals. The square root of, we'll say the nth root, because this makes it more general. The nth root of a times the nth root of b can be written out under one radical, the nth root of a times b. And so what you can see here is what we did kind of in reverse order. We started out with something that could be expressed as a product, as we did here, and we broke it up into two separate statements, one of which we could simplify, right? So this is kind of what we did when we were simplifying it, but looking at it from the backwards perspective, this gives us the multiplication rule for radicals in general. Now, the key thing here that we have to have is that we have to have the similar index, and these have to match. But as long as those match, we can carry this out. So, for example, we could see the square root of 2 times the square root of 7 is the square root of 14. And since we can see 2 and 7 can't be broken up anymore, so they're prime numbers. We know that the square root of 14 actually is in its simplest form. In other words, there's no perfect squares for 9, which are the only two that are less than 14 that would go into 14. So this is actually in simplest form because we know it's made up of 2 and 7. And this applies with expressions as well, like x plus 3, right? So if I'm going x plus 3 times the square root of x minus 3, and those parentheses are mine, those don't necessarily have to be there. But as long as they're both square roots, which if there's nothing written, we assume that's a 2 there, then this would be the square root of the product of x plus 3 times x minus 3, which of course we know this is a product of a sum and a difference. And so that's x squared minus 9. Again, can't be simplified, and we can know that because, first of all, we can't break this up, this x squared minus 9 here, because we can see what it's made up of in terms of what its factors are, and neither of these factors are perfect squares. Okay, so now I'm going to go on to another page here. If I had something like, if that hadn't been x plus 3x minus 3, maybe it was x plus 3 times the same thing, x plus 3, you could see this would give me the square root of x plus 3 times itself, which, of course, the square root and the perfect square would simplify to give me the absolute value of x plus 3. And one thing you want to watch for in these exercises is once we, I don't want to make a blanket statement because all the books are different, and sometimes they throw in some random questions, so you want to be aware of it. But if they say, assume all expressions produce positive real numbers, then we don't have to worry about the absolute values, right? That's the point of the absolute value is to make sure that we're not going to break a rule here by plugging in something for x that's going to lead to something negative, right? Because then this rule wouldn't work. It would be a false statement, in other words. But if they say that x could be any real number, or the expression can come out to something that could be possibly negative or could be any real number, then we do have to watch for that absolute value sign. Now remember, the absolute value sign only happens when we have a even index with an even power while it's under the root, and then results in something that's being raised to the first power, right? And so that expression, x plus 3, is by itself, so it's kind of being raised to the first power, even though generally we wouldn't write that, but that's that even, even, odd. If we have that even, even, odd combination, then we have to put the absolute values if they haven't said something in the instructions that would, that's basically saying, it's a fancy way mathematically of saying, don't worry about the absolute values for these problems. We're not really quizzing you on that right now. And usually outside of the first time they ask you to practice it, that's generally how they set it up, so you don't really have to worry about it. So there may be times where you studied things like this and like they didn't say that, and I was always getting the right answers. Well, they didn't change it on you. All they did was really wrote it into the instructions. This is the little tricks that we as mathematicians sometimes will use to get out of having to do something. But unless you're really intimately familiar with it, a lot of times that can slip by you. So, so not only does this help us simplify radicals, but it also allows us to see what happens when we multiply. Now, I'm going to say, even though I'm going to make a different video for this, but when we do division, it's a very similar thing. Same idea. We can divide two radicals if, and in dividing them, we put the fraction, because usually they're presented as a fraction, as long as they both have the same indice, we can write it under one radical covering the top and bottom, and then simplify whatever is can be simplified within that fraction. All right, so for example, the square root of 200, we look for perfect squares that go into 200. Of course, 100 stands out. So this can be broken into 100 times 2. And 100, of course, is a perfect square. So that gives me 10 square roots of 2. Notice I don't have to worry about the absolute value stuff when it's not a variable. Right? The only time we have to worry about absolute values is a variable, because you could plug anything in for a variable. But 100 can't be negative because it's 100. and 100 is 100. So great. So let me give a couple of breakdowns for some actual like variables. So for example, let's say we have the square root of 50 x squared y. So 50 I know has a perfect square in it. So let's deal with the number first. 25 goes into 50, so that's going to be 25 times 2. So I'll write those as two separate radicals. And then the x squared also has, again, this is a square root. So there's two x's there that can come out. So we're going to write that as the square root of x squared. And then y is not something that I'm going to be able to simplify. So these two are the ones that will stay underneath the radical. They can't come out. But these two will be able to come out. So the 25 becomes a 5. This x, square root of x squared becomes just x. And because, again, we've got that even, odd outcome, we're going to put absolute value signs around that x and then the y. Notice I didn't have to put absolute value signs around the 5 because the 5, again, came as the square root of 25. There's no reason for me to clarify that with an absolute value. It's only the x that I have to put that absolute value around, not the numbers. All right, let's look at, oh, here's a good one. The cube root of negative 72. Now, because it's a cube root, we can actually have negatives. If that was a square root, we'd just say, oh, there's no real solution here. But with any odd indexed radical, we actually can have negatives come out of that. And if we have those negatives, we do want to take them out if this can be simplified where it can come out. So 27 is a little bit harder to see this, but what we want to think of is what perfect cubes will go into 72, sorry. So our first perfect cube would be 8. And 8 does go into 72 9 times. So cube root of negative 8, I'm going to put first. And then what we have left is 9. And so we'll put cube root of 9. Now you may be tempted there as well to take 9 out, thinking, oh, it's, 3 squared is 9, but this is a perfect cube. Always really be conscious of, as you're working these out, to continue to carry forth the index. Otherwise, people tend to get confused there. And we'll think of it, your brain will see the square root of 9, and you'll want to simplify that. The cube root of negative 8 is actually negative 2. So negative 2 cube roots of 9. Here's another sort of non-square root. We'll do a fourth root here of 162 x to the 6th. Now, you may wonder, you probably thought on that last problem that I just knew that 8, is going to go into 72, and so I just grabbed it, right? But really systematically in my mind, what I was thinking was, I start with the lowest number cubed, which of course the lowest perfect cube would be 1, but 1 doesn't really help us simplify anything. And so I actually went to 2 and thought, what's 2 cubed? 2 cubed is 8. And so 8 is the first number I wanted to check. If that didn't work, I would go to the next perfect cube, which is 3 cubed or 27. And I would see if 27 went into that. And then if that didn't work, we would go on to the next one and so forth and so on. So now we're looking for perfect fourths, right? In other words, a number that is, that when raised to the 4th power gives us a perfect fourth. And so we want to start with 2. Well, 2 to the 4th is 16, but 16 does not go into 162. And so then we go to the next perfect cube, which would be 3 cubed, which is actually 81, right? And these are things you could do on your calculator as you're to check them, right? So we're going to go the fourth root of 81, and 81 times 2 is 162. So, and then the x to the fourth is, so for x to the sixth, there's 4 x's that I could take the fourth root of, right? In other words, x to the sixth I could rewrite as x to the fourth, and again, fourth root, times the fourth root of x squared. So I broke up my 6 x's into 4 and 2, a group of 4 and a group of 2. Why? Because I needed groups of 4 in order to bring it out from underneath the radical. And so what you want to think of is there an exponent I could turn the 6 into, right, starting with that, so that it's divisible, so that this is divisible by the index, right? So if I had x to the 8th, then I wouldn't need to break it up. You know, if I had x to the 8th over here, I wouldn't need to break that up because 8 would be divisible by 4. And so when you're doing these, that's kind of what you're doing. You're dividing the power here by your index. And if you think back to the previous, when we were rewriting these as rational exponents, this should kind of make sense to you, because if you remember that when we had the nth root of a to the m, and sometimes maybe they have those backwards, but I think that's generally how you write it, this can be rewritten as a to the m over n, right? So it's this, oops, it's this divided by whatever we have here, right? And that's how we re-express them. And I'm not sure if I'm gonna, I think it's recording, so you may not have been able to see that with my video in the way. I'm not really sure, but m over n. So at any rate, I'm gonna hide that so it's not even in the way. I'm not really sure quite yet if this records the screen. I think it does, but I'm not sure if it records my iPad screen or if it records the screen on my computer. Like, I haven't figured this stuff out yet. I'm kind of in the process of learning. All right, going back to what we have here then. The fourth root of 81 is 3, because 3 to the fourth gives us 81. And then the fourth root of x to the fourth is x, and that's x to the 1. So again, we have the even, odd outcome there. So we need to put absolute values unless it says that x is going to be a positive number. And then we have left over the fourth root of x squared. Great. So there's a few examples to kind of help you. What I found is really helpful when working through these is to have a piece of paper that sort of details the perfect squares. And, you know, like, so like 2 squared is 4, 3 squared is 9, 4 squared is 16. And then maybe the perfect cubes and the perfect fourths. You just want to get kind of familiar so you can spot those, especially the cubes. And cubes usually are the highest we go, but sometimes we go to the fourths or fifths. So you kind of want to just be familiar with those as much as you can. Okay, so I want to lay out some of the things that we don't do. I call these the do not do these rules. So I'm going to write that out here. Don't do these rules. Okay, and so these are things you want to watch out for. These are common errors that people make. So for example, let's just take something that's start out with written as a power. So like, let's just say 1/2, Right. So we saw previously, and you may remember this from when you were working with powers and the power rules, is that we don't take a sum or difference and we cannot distribute the power to them, right? I can't take this 1/2 and take it to the C and take it to the B and take it to the A, right? For example, if we have x plus 3 squared, this doesn't translate into x squared plus 3 squared, right? Those are not equal. In fact, the way we want to do x plus 3 squared is to take x plus 3 times itself, and we FOIL that out, right? We go x times x is x squared, and then x times 3, and then we do it for these two as well. And we end up not with x squared plus 9, but x squared plus 6x plus 9, right? And so when we have it in forms like this, we wouldn't do that either. If we have 3 of them raised to a power, we don't distribute that power. It doesn't come out correctly. And so that also translates over to what we do with radicals. If I have this, in fact, can be rewritten as the square root of a plus b minus c, right? Those are equal. But this does not equal square root of a plus square root of b minus square root of c. We can't rewrite it that way. So that's a do not do this. And that goes or is similar to the rule we saw over here where we took a plus b squared and we say this is not equal to a squared plus b squared. It doesn't work that way. In fact, if you have an a squared plus a b squared, it can't be factored either, right? Factoring is when we kind of take something that's a sum and we rewrite it as a product, right? So this is a sum of 2 perfect squares. Well, that actually doesn't have a factored form. It's not equal to a plus b squared. But it's a very tempting thing to do. That's why I even lay these out and call these the do not do this rule, because it doesn't work, but everybody wants to do it. But what we can do is break up products. And so for example, let's just do another one of these. Square root of x to the 7th, y to the 11th, and z to the 8th. Okay, well, with 7 here, I know that 6 of those can come out, 6 of those 7, because 6 is divisible by 2. So I'm going to take 6 of them out, write that as x to the 6th, that's the square root, times, actually, let's go ahead and just write these under one radical, so times 1x. So I broke the x's into a 6 and a 1. And similar with the y's, I want to break y up so that the power is divisible by 2. So y to the 10 times another y. And then z to the 8th doesn't need to be broken out because 8 is divisible by 2. All right, so breaking these up, this would be x to the square root of x to the 6th, square root of y to the 10, square root of z to the 8th. And then what we're going to have left with is the square root of x and y. So that gives me x to the 3rd, y to the 5th, and z to the 4th, square root xy. And if we were needing to use absolute values, the absolute values would need to go around the first two. It wouldn't have to go around that one because z to the 4th is an even power. So any value of z would already be raised to an even power, which would make it positive if it was negative. But if these were negative, then raising them to the 3rd and to the 5th power would result in something still being negative. So we have to put this around absolute values if x, y, or z can be any real number. Okay. I'm going to take you to one more example here with multiplying radicals, and that's you being given something that's, as we saw on the previous slide, like 3x squared minus 6x plus 3. This is the type of thing you would be tempted to break up, right? And to violate the do not do this rule. Can't do that. This is written as a sum and a difference of 3 different terms. And we cannot break up sums or differences. We can't distribute powers to sums and differences. And we cannot break up a radical into separate sums and differences. But what we want to do is to rewrite this as a product if we can. And this involves factoring, right? So first things first, I look at the 3 terms and I can go, 3 can come out of this. 3 is a common factor for each one of these. So I'm going to rewrite this, and because you always want to look for a greatest common factor first. As far as x's go, these 2 have x's, but this one does not. So we can't factor out any x's, but we can factor out a 3. And a lot of times if you do that, it makes this a lot simpler to factor. And I screwed up there. That should not be a 3, that should be a 2. And then this is factorable. In fact, what we're really looking for, and generally if they're giving you problems like this, you can look for perfect square trinomials, which is what we have here, where the middle term is twice the product of the roots of the first and last terms. So the root of x squared is x, the root of 1 is 1. So 1 times x doubled would be 2x. So this can be rewritten as x minus 1 squared, which now I can take the perfect square of this, except for the 3. The 3 remains. See, notice how I rewrote it, just like we had up here, is a bunch of products, x times y times z. Now this is written, this is why we know something is factored when it's written as a statement of multiplication. 3 times this expression squared. So it's now written as not a sum of terms, but as a product. And we can break up that product, right? We can break it up as square root of 3, which can't be simplified, and the square root of x minus 1 squared. And so this comes out. So we'll write it out front. We generally want to write these, if they've come out of the radical, you'll notice I always write them out front. It's tricky. You want to do that with radicals because sometimes people get sloppy. But let me get to that here in a sec. So anyway, x minus 1, we'll put absolute values around that, times the square root of 3. This would be the factor, or the square root of that. Now, why do I say write, once you've taken them out of the radical, write them out front? It's one of those things where it's not wrong if you write that, because multiplication can be in any order, and truly this is a multiplication. It's a multiplication of this times this. But we tend to write things out front, especially with radicals, because, for example, let's say you have the square root of 3x. So you have square root of 3 and x, but people get a little sloppy sometimes with the line up here. And so if you look at this, it kind of looks like, wait, is the x underneath the square root, or is it not underneath the square root, right? Some of you all, I'm not going to call you out, but I am right now, can get a little sloppy when you're writing things, and you can begin to confuse yourself. If you're sometimes sloppy with your work, I raise my hand. I've gotten better over the years because I have to, otherwise students were like, what did you write up there? But if this was the square root of the product of the square root, if this was the product of the square root of 3 and x, I would want to write that as the square root of 3, square root of x times the square root of 3, just to show that x is not under that radical, and that it's outside of the radical. All right, well, I hope that helps. I'm going to do another video for the division part of this, but this concludes the lecture for the multiplication of radicals.